Hi everyone, I'm Noafrika from Materials Science student would like to share with you the shape memory alloy. Firstly, what is definition of shape memory alloy? Shape memory alloy is a group of alloy that shows the ability to return to their original shape or size. Alloy appear to have memory when they are subjected to heating or cooling. There are two phases of shape memory alloy. First is monazite.
Monazite is relatively soft and it is easily deformable phase, which exists at low temperature monoclinic. And then austenite. Austenite is a phase that occurs at high temperature, having a crystal structure and high degree of symmetry qubit.
There are two types of shape memory alloy. Firstly is one-way shape memory alloy.
One-way shape memory alloy is a material which exhibits shape memory effect only upon heating.
And then two-way shape memory alloy.
Two-way shape memory alloy is a material which shows a shape memory effect during both heating and cooling. Shape memory effect. The change of shape of a material at low temperature by loading and regaining of original shape by heating it. The shape memory effect occurs in alloy due to the change in their crystalline structure with the change in temperature and stress. While loading, twin monazite become deformed monazite at low temperature. On heating, deformed monazite become austenite shape recovery. Next is superelasticity. Unlike the shape memory effect, superelasticity occurs due to stress-induced phase transformation without a change in temperature. The load on the shape memory alloy change austenite phase into monazite. As soon as the loading decreases, the monazite begins to transform to austenite. This phenomenon of deformation of a shape memory alloy on application of large stress and regaining of shape on removal of the load is known as superelasticity. Damping properties. Damping hysteresis is one of the important properties of shape memory alloy. They have high damping characteristics because of their ability to transform mechanical energy into thermal energy. This irreversible energy transformation allows the material to resist shock and absorb vibrations. To have a good damping effect, the shape memory alloy has to be in the dual phase domain, monazite plus austenite. In the dual phase domain, shape memory alloy possess high damping capacity due to the stress-induced monazite transformation and reorientation of monazite variance under the application of an external loop. The internal frictions determines the movement of interface between austenite and monazite, and thus allowing the dispersal of a large amount of mechanical energy.
There are three characterizations of shape memory alloy. Firstly is DSC.
Differential scanning calorimetry (DSC) testing is the most popular thermal analysis technique used to evaluate phase transformation temperatures and the latent heat related to them. It measures the difference in the amount of heat required to increase the temperature of a sample and a reference as a function of temperature. Hence, it is also widely used to measure the starting and ending temperatures of multi-state transformations. Next is electrical resistance measurement. This technique is useful to assess the dependence of electrical resistance on temperature and mechanical loads, and electrical resistance is used for determining transformation temperature values as well as for tracking down phase, compositions, and microstructure change induced by external thermomechanical conditions. Antonucci et al. Compare the electrical properties of two alloys, one with NR phase and one without it, on temperature variation based on figure 3.17. They found that ER as function of temperature shows similar behavior for both the two alloys during cooling. A rapid large increase is corresponding to the transformation from austenite to the R phase, based on figure 3.18. The comparison between calorimetry and electrical measurements points out the importance of temperature dependence of latent ER for identifying particular transformations that otherwise could not be identified using calorimetry technique. ER measurements in fact have proved to be a good probe for identifying the R phase and its start and finish transition temperature. Moreover, the presence of a mixed phase consisting of martensite and the R phase has been detected from VR measurement, but not from DSC analysis. Last is neutron diffraction technique. These tests are used for detecting crystallographic changes on phase transformation and can be carried out during heating or during the application of a magnetic field to monitor structural changes in situ.
There are numbers of processing techniques for perform shape memory alloy.
The classifications of processing of shape memory alloy are divided into four classes, which are powder metallurgy processing, additive processing, thermomechanical processing, and mechanical processing. Powder metallurgy processing is a conventional method of material processing in which the metal powder is processed to obtain final product without any material removal. Various powder metallurgy techniques such as sintering, hot isostatic pressing, metal injection molding, self-propagating high temperature synthesis, and spark plasma sintering are reported for different shape memory alloys in the large number of literature. Shape memory alloys of lithanol, copper, aluminium, nickel, manganese, copper, aluminium, nickel, and iron, manganese, silicon, chromium, nickel are processed and investigated by different aforementioned powder metallurgy techniques. Additive processing is an advanced manufacturing classification of processing material by adding successive layers of the material to prepare a final part or product. Addition of metal layer is done with the help of metallic powder that is processed with the help of well-controlled processing technique. It is also popular as rapid prototyping or rapid manufacturing. Additive processing is capable to produce intricate parts and geometries without any material removal. It is a sustainable manufacturing approach due to having advantages of cost-effective processing, material savings, excellent energy efficiency, and environmentally friendly processing. Various additive processing techniques such as selective laser sintering, selective laser melting, laser engineered net shaping, and electron beam melting are reported for shape memory alloy. Next processing is thermomechanical processing. Is a category of fabrication processes that undergo mechanical deformation or plastic deformation process along with thermal processing effects. Friction stir processing, hot rolling, fogging, and heat treatment and extractions with heat are examples of thermomechanical processing. Last classifications of processing is mechanical processing. Mechanical processing is a category in which the processing is done by mechanical loading that causes material deformation and leads to change in properties. Mechanical processing such as equal channel angular extractions, cool fogging, and cool drawing attempted for shape memory alloy.
There are many applications of shape memory alloy. One of the applications is microvalve.
One of the most common applications of shape memory alloy is microvalve or actuator. The electrical signal initiates an action. When an electrical current of 50 to 150 milliampere flow in Natanol actuator, it contracts and lifts the poppet from the orifice and opens the valve. The other applications of shape memory alloy, which is nitinol, are used to make eyeglass frames and medical tools. When the eyeglass frame in hot water, it can be bent because it made from super elastic nitinol and provide good comfort and durability. Moreover, shape memory alloy have been used in the aircraft industry. NASA has applied a new technology in flight that allows aircraft to fold its wings while in the air. It recently tested a new lightweight shape memory alloy to enable moving the
outer portions of the wings up or down in flight. The alloy is triggered by temperature and the wing can fall between 0 and 70 degrees. The space agencies having flexible wings could make flight more aerodynamic for both subsonic and supersonic aircraft. Systems with this new technology may weigh up to 80% less than the traditional systems, NASA added.